Usually I got it down by the third time. Find the area bounded by the graph of that cardioid. This graph's from 0 to 2 pi. So this is where it comes into play that if you don't know how many radians it takes to graph it, you're going to be in trouble. So everything graphs from 0 to 2 pi except for circles and odd roses. Circles and odd roses go from 0 to pi. Now, if the area of a sector of a circle is 1/2 r squared theta. So we end up integrating 1/2. We do the r squared, but the theta becomes d theta, because we want to treat this cardioid like a circle, and it's not circular. You think about if your circle was out here, radius, the circle looks like this. But if we have this angle from here, this tiny little angle, that's not acting like a circle. That's acting like a cardioid, but we want it to act like a circle. So if we make that angle small enough, it will be acting like a circle. Just like if we have a curve, if we zoomed in close enough, it would look like a line, even though it's a curve. So this theta becomes d theta. Now in order to integrate this, we know what r is. We're going from 0 to 2 pi because we're finding the area of the entire thing. And we're going to go 2 plus 2 sine theta squared d theta. Now before we get into the mechanics of it, I want to talk a little bit about how this finds the area. And if we have this curve, right, and we wanted to find the area from 1 to 10, really what we did is we talked about these rectangles. And we're finding area really we're accumulating area from left to right. And so we're working our way that way. And we're accumulating area as we go across, like that, in a kind of a linear fashion. This one, we're accumulating area, we're not going across it like this. We're actually going in a circle. And so we're finding areas like this, and we're going around the circle from the pole. So we find these tiny little angles, and we're treating it as a sector of a circle, really is what we're doing. And we're coming all the way around, and we're finding area. Right here, there's an area of 0, and then we finish all the way around to 2 pi. So that's how we're accumulating the area on a polar graph, because these graph more in a circular fashion rather than a normal function that kind of graphs from left to right. So that's what's actually happening. It's actually really important to know that later in the problems that we're going to do. Let's do this. Let's do the mechanics of this problem now. We have 1/2, 0 to 2 pi, 4 plus 4 sine, not cosine, 4 sine of theta plus, it's 4 and 4, that's 8. Boy, I hope I haven't been doing that wrong all day. 2 and 2 is 4, but there's 2 of those, right? So 8 sine of theta plus 4 sine squared theta d theta. I have written over on the board, and if you're watching this video, I have it on the board, and I'll write the one that we're going to use. We have the double angle formula for sine, cosine, and then if you solve for cosine squared, you get this one. You solve for sine squared, you get this one. Here's your Pythagorean identities, and we'll talk about this one down at the end. So sine is the same as 1/2 minus 1/2 cosine of 2 theta. We can make that replacement. And we can't integrate sine squared directly. We have to make the replacement. 1/2, 0 to 2 pi. 4 plus 8 sine plus, now if we run the 4 through there, we get 2 minus 2 cosine of 2 theta d theta. And now we're actually ready to do the integration. 1/2, 0 to 2 pi of, I'm doing the integration. I don't want integral here. 1/2, 6 theta, because 4 and 2 is 6, so I combine those right there. Minus minus 8 cosine theta. And then over here it'd be minus sine of 2 theta from 0 to 2 pi. There's the antiderivative. Say it again. Well, the derivative of sine is cosine, right? Am I good then? I think I am. Okay. So 12 pi, cosine of 2 pi is 1. Sine of 4 pi is 0. 0 cosine of pi is 1. So minus 8 minus 0. But then we have 8 plus 8. So half. I'm looking at 6 pi. When you get that written down, I want you to grab your calculators if you want to play along. Practice this a little bit if you want. Oh, I don't want to graph. Can I quit? Okay. I don't think we graphed today. I don't know why I hit that. All right. Out of there. I wanted to clear, not graph. Let's go back to the beginning right here. We'll go 0.5, math number 9. I got it. Math number 9. 0 to 2 pi of, we're going to go 2 plus 2 sine of x, or theta, squared dx. Now, if we want to know if that is a multiple of pi, here's a little trick I just wanted to show you. I think it's obvious. I hope it's obvious when I say it, but I don't know if you'd have been able to think of it. Just divide by pi, and that should say 6. So it is a multiple of pi. It's 6 pi. All we got to do now is hope we set it up right. I know I did the integral right, but hopefully we set the integral up correctly. I did get the right value for that integral, though. Now, whether we set it up right, hopefully. Find the area of one petal of that rose right there. So I need to know where this petal begins and ends. Now, I'm pretty sure it's going to begin at 0. So 0 will count by pi over 6s. 1/6, 2/6. Now, the sine of 0 is 0. The sine of pi over 2 is 1, so that's 2. And then the sine of pi is back to 0. So I got it. So at pi over 6, it's out here. And then pi over 3, we've completed 1. So we're going to integrate from 0 to pi over 3 of 1/2 4 sine squared of 3 theta d theta. That's one petal. Now, let's do this one by hand because I need to talk about 3 theta. Well, we know that cosine of 2 theta is equal to 1/2 minus 1/2. No, excuse me. Let me rewrite that. We know that sine squared theta is equal to 1/2 minus 1/2 cosine of 2 theta. We know that relationship right there. The problem is we're replacing sine squared of 3 theta, not sine squared of theta. But the good news is I can put a 3 theta in for that. I can replace it. I can put a 3 theta in for theta, make that 6 theta. So what we end up with, when we distribute the 4 through, is 2 minus 2 cosine of 6 theta. That's the replacement we can make when it says sine squared of 3 theta. 4 theta would be 8 theta, 10 theta would be 20 theta, and so on. The good news is we can just make that replacement. That's legal in Nebraska, no problem. So we integrate 2 theta minus 1/3 sine of 6 theta from 0 to pi over 4. Oh yeah, somehow I got it to be a 4. 3 here, 3 here, thank you. All right. 1/2 of 2 pi over 3 minus sine of 2 pi is 0, minus 0 minus 0. So it ends up being pi over 3 is the area of one petal of that rose. So I grabbed this one mainly because of that goes to that right there. That's the little trick you got to know for this one. Everybody good? Everybody got it? All right, here we go. Find the area of one petal of that rose right there. There's like a specific reason I picked for each of these. This one is because I want to use symmetry for this. Now, it's one petal. And if I decide, all right, how far does one petal go? Well, we have theta and r. 0, I'll count by pi over 4s. Pi over 4, 2/4 is pi over 2. I think I'll stop there. Cosine of 0 is 1, so that's 4. And then pi over 4, that becomes pi over 2. That's 0. And actually, that's all I need. Because I'll go here, out at 4. And then I have a 1/2 a petal right here. I have this much. If I find the area of that, all I have to do is double it because I see symmetry here. Above the x-axis, below the x-axis. So this is how I would do this one. I would take time, I would go 2 times a 1/2 integral from 0 to pi over 4 of 16 cosine squared of 2 theta, d theta. Now let's talk about the options that you would have on this one. If I go backwards, if I go forwards pi over 4, I could go backwards pi over 4, and then I'd have the entire petal. So I could also put it as negative pi over 4 to pi over 4, and I wouldn't have to double it. I could write it as 16 cosine squared of 2 theta d theta. The only bad part is you have to plug in negative pi over 4, which wouldn't be horrible, but I'd much rather plug in 0 than deal with negative pi over 4. But that is an option. All right. 0 to pi over 4, those cancel. This is 1/2 plus 1/2 cosine of 4 theta. I can make that replacement right there. Then if I run the 16 through, it's 8 plus 8 cosine of 4 theta. And now we integrate. We got 8 theta plus 2 sine 4 theta from 0 to pi over 4. So we have 2 pi, that's 8 times pi over 4. Sine of pi is 0. 0 plus 0. And when I choose to plug in 0, you end up with a lot of it being 0. It's just very nice to plug in 0. But sometimes you have to use a little symmetry to get that 0 in the problem. Questions on that? All right. Find the area of one petal. Got it. What if we throw 2 shapes into this? Set up and then use a calculator. We haven't really been finding answers. We'll do that on this one. We did find answers, actually. Find the area inside r equals 3 sine, and outside that dimpled, no, that's actually going to be convex. All right, what are we doing? Inside the circle and outside, this is a dimpled. No, it's convex. Convex limacon. All right, inside the circle, inside this one, but outside this guy. So we're looking at that area right there. And we have to think about, well, how do we get these areas? Where is it sweeping through in a circular fashion to get this area? And we don't start at 0 because there's no area over here that we're looking for. We don't start looking at area until we get right there. That's where we start getting area, right at that intersection point. So 3 sine theta is equal to 2 minus sine theta. 4 sine, and sine is a half. Sine's a half at pi over 6, and then again over at 5 pi over 6. But when we get past this intersection point, now what about this area? If this was a very, think of this not as a line. Don't think of it as a line. Think of it as a very, very narrow angle. Think of it that way. Extremely narrow angle. I would want the area all the way to the circle minus the area to this convex limacon right there. I want to subtract out that area. So I think I would do this. I would go 2 times a half. I'd go from pi over 6 to pi over 2. And you don't have to do it this way. You could go from pi over 6 to 5 pi over 6. And if I'm plugging into the calculator, I would have no problem going from pi over 6 to 5 pi over 6. I'd rather plug in pi over 2 if I had to do it by hand. All right, circle minus circle minus that convex limacon. So we have 9 sine squared theta minus 2 minus sine theta squared d theta. There we go. We have it set up. I used a little bit of symmetry, but if you don't like the symmetry, and I'm just plugging this in the calculator, we'll go from pi over 6 to 5 pi over 6. No problem. We could do it that way too. All right, let's do it on the calculator. A half, math 9, pi divided by 6, to 5 pi divided by 6, of 9 sine squared. Oh, whoops, that's not how you do it. I got it. I need the variable. Then squared. Minus 2 minus sine of x squared. All right, here we go. Let's see what kind of decimal value we get. We get that nasty decimal. Let's see if the multiple of pi doesn't seem to be yet, but that still could be a fraction. So we go math, fraction, nope. Even if it is, the calculator doesn't seem to be able to handle it. So we'll go 5.196. That's the best we can do if we're using a calculator. It either might not be a multiple of pi, or it's just a fraction that the calculator just doesn't seem to recognize. Subtraction, just like we did in washers. Remember seeing this? Pi integral of big R squared minus little r squared, dx or dy. It's the same concept. Big area minus little area. All right. We're going to do this one not only the way I wrote it, but I think I want to add one in, and we'll just set these up. That way we can go a little quicker. Find the common area inside the circle and inside the cardioid. All right, can you shade that area in? Where do you think that is? Where do you think it is? I bet you know it. Not that tricky of a question, I don't think, but if you get it wrong, that's fine. We're just seeing this for the first time. All right, I saw most of you had it. It's in here. Here's the common shaded area right there. This one is a little different. Now, if you take any little, tiny little angle, and I mean from the pole, and if I draw a line, I'm not considering that a line. I'm considering a very narrow angle. There's no subtraction. I'm not finding this area. I'm finding the area of that shape right here. And we can go from 0, and we can follow the cardioid, following the cardioid, till we get to the intersection point right there. So let's get that intersection point. 2 cosine theta equals 1. Cosine is 1/2. That's pi over 3. So we always make these nice. You know, we're not going to go with crazy angles. That's not necessary. So if I start out at 0, use symmetry here, and find the area of this shape to pi over 3, that gets it all the way to here, right there. So I'll have this right there, that piece of pizza right there. I'm using symmetry, so I'm going to double this. 2 times 1/2. I went from 0 to pi over 3, and we decided that it's following the cardioid. 1 plus cosine of theta squared. It's following that. But now we have this piece left over. I haven't found any of this yet. But now if I draw a line from here to this piece, now it's following the circle. So it's not subtraction, it's actually addition. 2 times 1/2 integral of 9, I'm running out of room, cosine squared theta d theta. So that one follows the cardioid, then it follows the circle. It's not following them both at the same time. Not that one. Ooh, I drew a mess up there, didn't I? Any questions on kind of understanding that? You got to be able to see it, though. That gets a little tough. All right, now, if I said this, I kind of want to include this for next year. What should we say? Find the area. Let's go outside the cardioid and inside the circle. Set up, but do not evaluate. Evaluate, just save some time. I assume you know how to plug these into your calculator. All right, try that one. Help each other out if you want. Talk about it. Compare answers. We can help each other. So circle minus cardioid plus cosine. There it is. There it is set up without evaluating. Now I use, go ahead. Okay, go ahead. Oh, yeah, same thing. And that's cosine squared of theta, d theta, like that. Yep, 0 to, same thing. All right, yeah, so we want to find this area right there and then double it, and that gets this area right here. And so I'm going to go from 0 to pi over 3, but if you draw one right down the middle, we're finding kind of area in between, right? So we want all of this area minus the inside one. That gets us in between. There is an issue on the quiz that we're going to take that, not a lot, but the biggest mistake that's made on this problem on the quiz is the following. Do I have your attention? Because I said quiz? I hope so. Here we go. Pi over 3 is a half at pi over 3 and 5 pi over 3. They're halves of both. Now, if you said, all right, well, I'm not going to use symmetry, and some of you won't on the quiz, and that's fine, because we can get the answer whether we use symmetry or not. If you say that I'm going to use the angle from 5 pi over 3 to pi over 3, from here to here, there's a huge problem with that, because that's not how it goes. If you go from 5 pi over 3 to pi over 3, you're actually going this way. Do you see that? You're going the wrong way. Now, if you want to go that way, good. That's awesome. But if you actually want to start here and start it at 5 pi over 3, what are we actually going to if we go this way? What is this? It's not pi over 3. From here to here would be 7 pi over 3. 5 pi over 3, 6 pi over 3, 7 pi over 3. So you could do this, but I get this on the quiz, and that does not get you the right answer. That's the wrong way. It's the wrong direction. It feels good. It's like, wow, that looks really good. But it's really, really wrong. Because we're already at 5 pi over 3, so if you're going to go to pi over 3, that would be going backwards. I think I made my point. Everybody get it? Any questions on that? All right, hopefully you don't do that now. Hopefully I've cleared it all up. Inside the 4-petaled rows and outside the circle. Set up, and I'm not even going to find the value. We're good. Can you graph that? Graph the rows. And you don't have, if you got to make a chart, go ahead. I certainly wouldn't make the whole chart. That's not necessary. Maybe you don't need the chart at all. I'll draw a little bit of it. I think most of you have it. If I did have to draw a little bit of chart, I would just do, if I do draw a chart, I'm just going to draw a little bit of it. I'm going to go 0, count by pi over 4s, 1/4, 2/4, and go, well, cosine of 0 is 1, so it starts at 4. Pi over 2 is 0, so it goes from 4 to 0. And then it would go like this, and then it would loop around like this, and then like this, and like that. So we expect 4 petals when we have an even rows. Odd rows, we'd expect the same amount. All right. Now I got to put the circle in here. There's the circle with r equals 2. Now, outside the circle, inside the rows. Inside, outside. That's right here. I'm just going to draw, if I can find the area of this piece right here, right there, there's 1, 2, 3, 4, 5, 6, 7, 8 of those. There are 8 of those little halves. That's the way I would do this. There are other ways. 8 times 1/2 integral from 4 cosine of 2 theta is equal to 2. So cosine of 2 theta is equal to 1/2. Divide by 4, 1/2. Well, cosine is a half at pi over 3. And there's another one at 5 pi over 3 if you want that one. So the theta that I'm looking for is pi over 6. I could use 5 pi over 6, but all I really need is the pi over 6. This intersection point right here is pi over 6. That's what I need. So to get that tiny little piece, I integrate from 0 to pi over 6. 0 to pi over 6. Now, we have to decide, do we use subtraction or do we use addition? Is it following one curve and then following another, or is it in between? And this one's in between. If I draw one angle, one tiny little angle right there, I want all of this area minus that little area right there. So all of the rows minus the circle. And don't forget to square it. It's always squared. That's why we have a 4 at the end, not a 2. All right, there you go. There it is set up. Using lots of symmetry on that one. Using lots of it. Any questions on setting up that one? All right. What do we got? Is this the last one, or do I have one more? Oh, yeah, this is the last one. Find the area inside the circle and outside. Give it a try. Go. See what you think. I think we're ready for this one. Check my answer on that, will you? Tell me if that's right or wrong. So we have 6 cosine. Cosine's off to the right. 1, 2, 3, 4, 5, 6. Because I relate cosine with x. So we have that, and then a circle of radius 3. Something like that. And inside this one, to the right, but outside. So right there. So I need 6 cosine equal to 3. So theta equals pi over 3. So this ends up being pi over 3. Now, I love using symmetry for these because I get to plug in 0 on this one. So I'd rather do 0 to pi over 3. You could do negative pi over 3 to pi over 3. And then you wouldn't have to multiply by 2. I'd rather plug in 0 and have to multiply by 2. That would be my choice. That's what I'd rather do. Well, if you draw this line, we're going all of that area minus this area. So it's not following one and then following the other. It's following both at the same time. That's the outside one. Minus 9 d theta. There we go. What if I said one more, and then we'll be done, because we got a little bit of time here. So hang in there. Find how about the common area? Set up, but do not evaluate. I assume you can plug this into your calculator. What if we did this one? You can help each other out if you want. But now the common area would be here. there's a little trick to this one. I like this one. Wouldn't it be, if I use symmetry again, if we started at 0, so I go double the 1/2, start at 0, it seems to follow this circle, seems to follow this one right here. All right, it's going to follow it till it gets to pi over 3, and it's just going to be 9 d theta plus, then it's going to switch over to the other circle. So if you draw a line here to here, it's switching over to the other circle. The question is, pi over 3 to what? What is that? Pi over 2. It is pi over 2. Now, you're like, well, how am I supposed to know that? Well, this circle hits the pole where? Well, when the radius is 0. So when does this circle get back to the pole? In other words, 6 cosine of theta, when does the radius equal 0 again? Yeah. So cosine of theta equals 0. Theta is pi over 2. So now this one goes from pi over 3. This is when it switches at pi over 3 to pi over 2 of 36. Oh, I forgot well, I didn't need it, but 2 times 1/2 ends up being 1 anyway. I would have lucked out there. D theta. So on the graphs, you got to decide, are you sweeping through both at the same time and have to subtract? Or are you following one and then following the other? Sometimes that can be a little hard to decide. But I've given you, hopefully, some good examples of that. I'm going to save this because I like what I added. All right, there's the assignment. We have time to try a couple, so go ahead and grab your notebooks or wherever you put them. Let's try a couple. Oh. I don't want you to do all these by hand. I almost forgot to tell you. I don't know how often you actually look at my schedule here. But I wanted you to at least set up a lot of these, but not have to do all of them by hand. So I'll even leave this on the video. 43 to 59 odd. Let's do some by hand. So the first, 43, 47, 51, do I bounce around at all? I did bounce around a little bit. So it's not all in an order. So those are the ones that I picked. Hey, let's do these by hand. I want you to set these other ones up and then just use a calculator so that you're not doing all by hand. So I'll save you a little bit of time. That way we can practice setting them up a little bit too.